Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, I'll go through this 5070. This is equivalent to any 14 to 16 years old pure chemistry curriculum that students around the world are doing. This includes the IGCSE or the GCSE level chemistry. This particular topic is on environmental chemistry. It encompasses the chemistry of the air as well as chemistry of water as well. So in this first bit, we are supposed to describe chemical tests. So what is very important is this is talking about chemical tests. So it has to be some sort of a chemical change and not just a physical change. Although we'll definitely see some color changes as a result of these particular chemical tests that allow us to detect the presence of water. So water is a liquid, so we can use this thing called anhydrous cobalt 2 chloride or also anhydrous copper 2 sulfate. So what you would notice is that this thing contains cobalt 2 plus, or you can say cobalt plus 2 oxidation number. This thing is copper 2 plus, or you can say copper plus 2 oxidation number. What we know about these are transition metal compounds, and as a result of them being transition metal compounds, transition metal salts, they are colored. So they are colored solid. They also form colored solution. This will continuation from the properties of transition metals, where they form colored salt, colored compounds, not only as solid but also in solution. The other thing that is worth noticing is this thing called anhydrous. So anhydrous has been stated in the syllabus previously when we did reversible changes or equilibrium. Anhydrous meaning no water of crystallization. So that means the water of crystallization has been completely removed. When you have water of crystallization, it is what is called hydrated. Anhydrous is when you remove all the water of crystallization. So first bit, the test for water, we can use this white solid, which is anhydrous copper 2 sulfate. So do not get confused between the color changes. We know that copper 2 plus in solution. This was part of qualitative analysis, test for cations. Copper 2 plus is a blue solution, very commonly asked in electrolysis topic as well. But then copper 2 sulfate hydrated is also blue solid. When we crystallize copper 2 sulfate crystals from the solution, saturated solution. Of course, when we heat everything to dryness, where we went the opposite way from the hydrated blue solid, we remove all the water crystallization, we're going to get this white color solid for this anhydrous copper 2 sulfate. So going in reverse, these are reversible changes, and that is why I said we have already gone through this in the topic on equilibrium as part of reversible changes. So this is hydrated copper 2 sulfate, is a blue colored blue color solid, and then this copper 2 sulfate anhydrous, this is a white color solid. So if we have a piece of filter paper which is dyed with these anhydrous copper 2 sulfate, in the presence of water it will turn blue. So white to blue color there. We can also use something which is more obvious, that is using the anhydrous cobalt 2 chloride. This is COCO2. If you know anything about formulation, CO2 plus, Cl minus, 2 and 1 is what you call the valency, VALENCY, or the combining power based on the charges of the ions. And then we can do the crisscross, which is basically primary school cross multiply. It means how many of these ions you must have. You must have 1 cobalt 2 plus and 2 of these Cl minus. Oxidation number of the cations depends on the charge of the ions, so this is called cobalt 2. In the redox topic of redox, you're supposed to know that naming transition metal compounds require you to use this Roman numeral. This is cobalt plus 2 oxidation number, so we use this Roman numeral 2 to represent the name cobalt 2 chloride, COCl2. This is anhydrous. This is going to be blue solid. So this is blue in color, and then it goes to pink when it's hydrated. This is true for the cobalt 2 chloride. Although the copper 2 sulfate anhydrous is white, it goes to blue when it becomes hydrated. Be very careful not to get confused between the two. As the syllabus already said, you should be able to describe in terms of color changes the chemical test required. This includes writing balance equation there. The next bit of the syllabus basically asks you to describe how to test for the purity of water. So we know that pure substances will have fixed melting and boiling point. That is as stated in the experimental techniques topic. So we know that pure substances don't contain impurities. So that's why they have a fixed melting point and boiling point for their change of state, which depend on the structure and bonding. So melting point is the 0 degrees Celsius for the melting point of water. And then for the boiling point of water is 100 degrees Celsius. This is boiling point of water. We also know that impurities, when you add salt to ice, this will lower the melting point. So that means your ice will still remain as liquid, even at temperature below 0 degrees Celsius in the presence of impurities such as salt. And then we know that it will increase or it will raise the boiling point. Think about salt. When you add it to boiling water, the water gets a lot hotter than 100 degrees Celsius. It enables you to cook pasta. When you cook pasta, spaghetti, you tend to add some salt to the boiling water prior to cooking it. So we have this thing here called a heating curve. Heating curve was part of states of matter, kinetic particle theory. So this is when the temperature continuously increases. When the temperature continuously increases, we know that kinetic energy increase as the temperature increase. However, you have this change of state when the solid turning to liquid there. That is your melting process there. And we also have liquid turning to gas at the boiling point. There's the boiling process taking place there. At this particular temperature, the temperature remain constant for a bit for the change of state. So what we can say from there is basically, let me just get this straight. So temperature remain constant at the boiling point and at the melting point. And then this is to do with the heat energy is being used to overcome the forces of attraction between the particle. As for what these forces of attraction is, depends entirely on the structure and also bonding. And these were all part of Year 9 structure and bonding. If you have giant ionic structure, that means you will need a lot of energy to break strong ionic bonds, such that the ions become free to move from the solid state to becoming having degree of freedom, being able to move freely, and they can conduct when they become molten. But we also talk about, if we have giant metallic structure, we need to break strong metallic bonds there. And if we have simple covalent structure, we only need to break weak intermolecular forces of attraction. These are weak intermolecular forces of attraction between water molecules, which are simple covalent molecule. We can represent the model by drawing these kind of diagrams, showing each of these lines as a covalent bond. But typically, exam question asks you to draw dot and cross. We also can convert each single line to 2 electrons being shared. Covalent bond, 1 electron from each of the atoms. Oxygen being a group 6 element, we only use 2 out of 6 outer shell electrons. We still have 4 more on the oxygen, showing only the outer shell electrons because the inner shell electrons are not used for covalent bonding at all. So here temperature increases. The ice particles, the ice, that is because below 0 degrees Celsius, you're still ice particles, they vibrate faster. The ice particles don't vibrate faster, no change in speed. So that means kinetic energy is constant there. So kinetic energy is constant, no change in speed, but then they are moving further apart as we supply the energy to overcome the force of attraction, which happen to be weak intermolecular forces of attraction between water molecules there. And then the liquid molecules of water, they can then slide past each other when everything has molten. And that means here they can slide past each other in the liquid state, but they also move faster as temperature increases until they reach the boiling point. Then they don't change in speed anymore as the temperature remains constant, kinetic energy remains constant, and the water molecules are just moving further apart as they are slowly turning to the gaseous state, and they become so far apart they move randomly, high speed in all directions, and they're moving faster and faster, having more and more kinetic energy as temperature further increases there. In this next bit, we're going to explain that distilled water is used in practical chemistry. So when you use the bottle of water in the lab, when you do practicals, to clean out your burette and your pipette prior to washing with the chemical itself, So usually we always use distilled water. To make up solution, we always use distilled water. We don't use tap water because tap water is a mixture. A mixture is an impure substance. It has got impurities. But then if we are supposed to test for cations or anions, we gotta make our solution distilled water, because if we use tap water, we have impurities, and those impurities might contain other dissolved ions, and that makes them impure. So in order to get distilled water, we do this process called distillation. So distillation setup include a thermometer where the bulb must be placed at the exit or at the mouth of this side junction here. Everything must be closed up. These are basically rubber seal because you are supposed to heat up the liquid. So you have seawater here. So these are basically the boiling process. As you boil this seawater, which contains salt and water, the water being a simple covalent molecules versus salt such as NaCl, we can think about the structure and also the bonding. Structure is simple covalent structure. These are all part of year 9 structure and bonding. NaCl between a metal and a non-metal. So these are ionic compounds. Their structure will be giant ionic structure. So when we apply heat, which one are we going to boil first? Simple covalent structure will have low melting and boiling point, and that is a result of us, making the molecules further apart. We're just supplying the heat energy to break the weak intermolecular forces of attraction. So we're just breaking weak intermolecular forces of attraction, and these are all part of year 9 structure and bonding fixed assay. Whereas for the giant ionic structure, we need a lot of energy in order to break strong ionic bond. Their melting point is going to range, in the range of thousands, or probably just under 1,000 kind of. So basically we are not going to boil it before we melt it. We are going to easily boil the water first. So boiling is the first step involved in distillation. We have this thing on the side arm called a condenser. What is very important is that the water is in at the bottom and the water is out from the top. If you have been in the lab, you try to put this the other way around, you wouldn't be able to get the water passing through all parts of the condenser unless you have the water in at the bottom. If you put the water in from the top, this top bit of the condenser will not be filled up by water, and that's dangerous in a condenser because you have very hot vapor. You don't want any part of the condenser to be, uncool, or to be not having been cooled down. That's quite dangerous. What you get collected here is pure distilled water, and the temperature on the thermometer should read 100 degrees Celsius as you collected this liquid out. So what we are going to do here is the second process. This is called condensation. Condensation is basically the vapor turning back to liquid. So two processes there, boiling and also condensation. And distilled water being 100% pure, that's what we use in practical chemistry. Doesn't contain any impurities or whatnot. I'll leave it there for this particular tutorial lecture. So I'll see you in the next part of these tutorial videos where we're going to continue to talk more about chemistry of water and chemistry of air in this environmental chemistry topic. Thank you for watching. Don't forget to click the button on the bottom right to subscribe to the channel, and do share the channel widely with friends, chat group, juniors, seniors, and other people if you think it might be useful to them. And do follow me at ptet.chemistry. That's ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. Thank you for watching again. I'll see you in the next tutorial video.